Good morning, afternoon, or evening. How y'all doing today? Welcome back to Mr. Morrow's Honors Geometry class. Today we are going to continue on our awesome journey of proving triangles congruent. And today we're going to extend it, and we're going to learn about CPCTC and circles. And I will tell you all that there needs to be known about everything here. So let's just go ahead and start with an example today, okay? If I tell you, given that triangle ABC is congruent to triangle DEF, okay? I kind of messed up here already. Sorry, guys. We know that B is congruent to E, but let me go ahead and just change this. Could I say that angle A is congruent to angle D? Would I be able to say that if I tell you that triangle ABC is congruent to triangle DEF? Yes, sir. Yes, you would be able to say that. If you remember the definition of congruent figures have the same shape, same size, equal corresponding angles, and equal corresponding sides. And that is known as CPCTC. And CPCTC stands for corresponding parts of congruent triangles are congruent. Yes, sir.
All you need to know basically was triangle ABC is congruent to triangle DEF.
That's absolutely correct, sir. Once I tell you that two triangles are congruent, or in your cases, once you guys prove that two triangles are congruent, then you know that all of the corresponding angles will be congruent and all of the corresponding sides will be congruent. And again, that is CPCTC. That is the abbreviation that we will use, so learn it. Corresponding parts of congruent triangles are congruent. And that's literally it for CPCTC. Okay? Now the second half of our journey today, we'll be talking about circles. I'm going to go over some basic circle stuff. Most of you, I know, you already know it. Some of you kind of know it. Regardless, we're going to sharpen up your circle skills today. Circles, okay? First of all, when you look at a circle, guys, and you have a radius, please remember, sometimes people get confused. A radius extends from the center to one point on the edge or circumference of the circle. Okay? And if you look here in this figure, I've drawn a bunch of different radii. Radius is the singular form. Radii is the plural form. So in this circle, I have a bunch of radii. One super powerful tool that you will use time and time again is knowing that any segment in a circle that extends from the center of the circle to any point on the circumference of a circle is a radius. And there's a theorem attached to this radius. And the Radius Theorem states that all radii of a circle, I put in parentheses there, within the same circle, are congruent. So that means that all of these red radii that I marked up here are all congruent. I could draw 5 million radii within the same circle, and they will always be congruent. Or if I have a value attached to them, they will always be equal. So it's really important to know what a radius is, and even more so to really grasp the concept that all radii within a circle are congruent. That does not mean that all radii of all different size circles are congruent. No, that's not what I'm saying. But within its own circle, all the radii within that particular circle will always be congruent. This is huge for the SAT. And we're going to be investigating this a lot more as we go on through the course. Now, the diameter, okay? The diameter is literally 2 times the radius. It is twice the radius. And a diameter is any segment within a circle that extends from one point on the circumference, that means the edge of the circle, the outside edge of the circle, to another point on the circumference going through the center of the circle. It's really important for you to understand that the diameter has to go through the center. Okay, so I have a point here on the circumference. It goes through the center and it attaches to another point on the circumference. If a segment goes from one point on the circumference to another point on the circumference without going through the center, then it is not a diameter. Okay? It is not. If that happens, it is what's called a chord. Okay? A chord is any segment within a circle. I'll leave both definitions up because I know you guys are working hard. There we go. A chord is any segment within a circle that extends from one point on the circumference to another point on the circumference, but chords do not go through the diameter. So if you see here the examples that I have here of chords, all of these are going from one point on the circumference to another point on the circumference, all of these. But none of these, my friends, are going through the center. That's what makes it a chord. So a lot of times, the question will come up, is a diameter a chord? By definition, guys?
Yeah.
Yes, because by definition, a diameter does go from one point on the circumference to another point on the circumference. But can I say that a chord is a diameter? No, because a chord, unlike the diameter, does not go through the center. So a diameter is a chord, but a chord is not necessarily a diameter. Okay? Does that make sense, my brothers? Alrighty. Let's move on. Now, let's remember a couple formulas here. Okay, again, I know that most of you know this, probably from last year's algebra or even in many cases from middle school. The area of a circle, okay, area of a circle basically is a description of how many square units inside of a figure or a space. That's what area is. And the reason I give you that definition is because a lot of times people just give you the formula, which is area equals pi r squared, and they just say go plug it in, and you know, you're plugging in numbers, but you really don't know what you're doing, why you're doing it. Think of it like this. A lot of you guys have tiles on your floor at home, and if you don't, just look down here on the floor of our very classroom. All of these tiles are 1 foot by 1 foot. That means that they're squares. All sides are equal. So right here, if I've got 1, 2, 3, 4 squares, that is 4 square feet. What that means is there are 4 1 foot by 1 foot squares in that particular figure or space. I'm sure you've heard your parents, you know, talking to their friends or whatever, and they ask, oh, how big is your house? What's the square footage? And they say, oh, it's whatever, 1,800 square feet. That literally means that you could put 1,800 1 foot by 1 foot squares inside of that space. If they tell you, I have an area that is 17 square centimeters. Well, that means literally that there are 17 squares that are 1 centimeter by 1 centimeter within that space or figure. Does that help out, guys, with the whole concept of area? It's how many square units inside of a figure or space. Now that we've gotten that out of the way, the formula for the area of a circle is pi r squared, where pi is going to be estimated at 3.14. And radius is r. Okay? A lot of times people ask me, Mr. Morrow, why is it 3.14? Well, I actually have an answer for you. Okay? If I take a circle, let me just go ahead and make a little circle here, and you wrap around the diameter around the circumference, okay, or actually the radius around the circumference, you're going to literally get 3 full segments with one little gap missing. That little gap is the 0.14. That's literally why it works and how it works, okay? A lot of people ask that, and it's a super valid question. Where did pi come from? Pi came from the Greeks. Why did the Greeks come up with this? Well, taxes. Geometry was invented because of taxes. And actually, the Egyptians were the first ones to really come up with area, because the Egyptians lived on the Nile, and the Nile River would flood every year. And sometimes after the flood, you had more land. Sometimes after the flood, you had less land. So the tax assessor would come out, look at your land, do measurements, find the area, and then he'd charge you based on your new land size. So you could thank the Greeks and the Egyptians for all of this. I know you guys are really happy about that. I know you're excited. So, all right. So let's continue here, guys. Circumference of a circle. Circumference is the distance around a circle. And any other figure, any other polygon, it's basically the perimeter of the figure. So the circumference, you can say, is the perimeter of a circle. Why isn't it called perimeter? Well, because it's not the perimeter. It's a circle. A circle's not a polygon. Polygon is made up of angles and edges. Circle's not a polygon. It is a figure, but it's not a polygon, so it's circumference. And the formula for circumference, there's two. You could use circumference equals 2 pi r, or you can simply use circumference equals diameter times pi. 2 times the radius is the diameter, so you could interchange this. It really doesn't matter. Sometimes they give you the diameter, so you use the second one. Sometimes they give you the radius, just multiply it by 2. You're still using the same formula. Again, where pi is approximately 3.14. That is an approximation, guys. Pi is an irrational number. There is no end to it. Sometimes you'll see in some books, they'll use the approximation 22 over 7. But 22 over 7 will also equal 3.14. Yes, sir? Okay. A circle has 360 degrees within it. Around it, there's a circumference, and they have to use that estimation. Without using that estimation, there's really no way to truly get an area or a circumference of a circle. So your question is extremely wise. Area of a circle and circumference of a circle is not an exact thing, is it? It's really an estimation. An extremely close estimation. It's an estimation that we use, and it's a fact, because we use 3.14, but we are cutting out pi. Good question. Good observation, son. Okay? So let's just do a couple little area ones, real easy. I want you to find the area of each figure and find the perimeter circumference of each figure. Okay, well, let's first find the area and circumference of the circle, which we'll call A. All right? So for A, my area equals pi r squared. So it'd be 2.5 squared times pi. And 2.5 squared, I believe, is 6.25. Okay. That's 6.25 times the pi button on any calculator will give you an area of 19.63 units squared. Area is always squared. And the circumference of this would be 2 pi r. Well, 2 times the radius of 2.5 is 5. So that would be 5 times pi. And pi we estimate as 3.14. So 3.14 times 5 would be 15.7 units, not units squared. That's why I do this. Area is always units squared, and circumference or perimeter is linear. It's only units. Yes, sir.
Say we get a problem like this, to write just like say 6.25 pi, you want us to write 19.6.
It depends. The question was, in a test or a quiz or a homework, can I just leave it in pi? It depends on the question. Sometimes even in the SAT, they'll say find the area in terms of pi. And then in that case, the first one would have just been 6.25 pi. Correct. I will tell you though. If I just say find the area and I don't say leave it in terms of pi, go all the way. Please. Yes, sir. Thank you. Thank you very much. Where did I get this 5 from? 2 times pi, times radius. Radius is 2.5 times 2. No, thank you, sir. We don't ask, we don't learn. There's no shame in that. Thank you, son. So does that make sense, boys? Now, okay. For the square here, okay? Let me show you a couple things, and hopefully this will enlighten you as far as area goes as well. This side is 4 units. This side is 4 units. Okay? Area of a square is the side squared. So that would equal 4 squared, which equals 16 units squared. Now, check this out, guys. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let me pause. Okay, sorry about that, guys. So if you saw here, I have 16 equal squares. That's what area is, guys. I have 16 squares of equal units. Okay? So I have 16 units squared. Let's say those are all, let's just say a millimeter. I have 16 1 millimeter by 1 millimeter squares inside of that square. And then the perimeter is all sides added together. So the formula for the perimeter of a square, because all sides are equal, is 4 times s, which in this case will also be 16, but it will be 16 units, not units squared. Again, I know this is simplistic, but I really wanted to drive this home with you guys. I really wanted you to walk out of here today really understanding what area was. Okay? And now, let's get to the part that you guys love. Okay, which are the proofs. Yeah, I know you guys love this part. All right. Let's do Let's do it. Okay. My given, I only have one given here, guys. I have a given that it's a circle. Circle P is the given. That's it. That's all I have. And P is in the center. Okay, that's why they call it circle P. Circles are named by their center point. So, circle P. That's given. I'm trying to prove that AB, segment AB, is congruent to segment CD. Well, let's think about the radii here that we have here, guys. I'm going to give you a little bit of a hint here on this one. Whoa, what happened here? Okay. If you notice, all of these are radii. What did we say about all these radii? That they're all congruent. So guess what? PA is congruent to PB, which is congruent to PC, which is congruent to PD. Because, very good, son, all radii of a circle are congruent. So now you know I love to make my little tick marks. That's congruent to that, and that, and that. Okay? Yes, sir. No, you do not have a triangle congruency yet, my brother. No, don't get mad at me. There's no triangle congruency yet. You're darn close, though, my brother. What do we know, though? Don't we know now, my brothers, that CPD, angle CPD is congruent to angle APB? Because of, not addition, vertical angles are congruent. Addition property, come on, man. Yeah, just put vertical angles are congruent. You could put vertical angle theorem if you so choose, or vertical angles are congruent. Very good, my brothers. Now we can go with a congruency statement, my man. Now I can clearly say that triangle CPD, I'll highlight it in red here, CPD is congruent to triangle, bless you, triangle APB. Why? No, how is that side, side, side? Thank you, very good. Good job, son. Side, angle, side. Why is it side, angle, side? Look at the figure there. I have a side, which is right here. Good questions, guys. This guy to this guy, that's a side. Then angle, then side. Labeling is the key to proofs, my friends. If you don't label, you're out of luck, Chuck. And now, how can I prove that AB is congruent to CD? That's exactly correct. CPCTC. Corresponding parts of congruent triangles are congruent. So, not only are we going to have to prove triangle congruency here, but then after that, we're going to have to prove that the corresponding parts of congruent triangles are congruent. Does that make sense, gentlemen? Any questions on that? Awesome. Let's continue then. Okay, bless you. Again, circle O is given. We also have that angle T is complementary to angle MOT, and we also have that angle S is complementary to POS. So, circle O is given. Okay? There's not much I can do from here, so I'm going to go ahead and say that OT is congruent to OS. Why? Why would OT be congruent to OS? No. Now you went crazy on me. You were great with the radii, but then you started saying bisects. No. All radii of a circle are congruent. Nothing was bisected there. I'm not trying to be rude, guys. You know that. I never will be. But be careful with your statements. Okay? All radii are congruent. Yes, sir. Can you say radii theorem? I guess. I'm not really happy with that, but I guess. Yes, sir. Go for it. Next, what would you do now? Okay, let's see. First, I'm going to go with angle T is complementary to MOT first. But what you said was perfectly correct. You're going to see why I went that route in a second, though. But you know what? This is a pretty long proof. So let me, like I've done before in the past, let me go ahead and move this down. Okay. And then hopefully that'll make our lives a little bit easier. Okay, so we have again that angle T is complementary to MOT, and before I do that, I'm always preaching about labeling, and I haven't labeled anything. OT is congruent to OS. This is a given. We also know that angle S is supplementary to, thank you, sir, complementary to POS, which is a given. All right? And now, I can say, what my boy had said before, MOP is congruent to POS because of vertical angles. Vertical angles are congruent. And now, if MOP and POS are congruent, what do I know about T and S, gentlemen? They're congruent. Very excellent, sir. Complements of congruent angles are congruent. Absolutely. You guys are on fire here today. Good job. So this is a double. This is a double. Now, what do I know about triangle MOT, bless you, and POS? Yes, sir? They're congruent because of angle side angle. Fantastic. And now what I'm trying to prove is that MO, segment MO, is congruent to PO. Well, MO would have to be congruent to PO because of CPCTC. Yes, sir. Ah. Why is it like that for number 5? Because Mr. Morrow made an error, and you were awesome enough to catch that. Thank you. That is MOT. You are 100%, and I apologize. That is my bad. Thank you, son. Thank you very much. That was a great catch. Thank you, thank you, thank you. Besides my little screw up there, does that make sense, gentlemen? You guys okay over there? Okay. Do you need me to make them a little bit bigger? Do you need me to make the notes a little bit larger, guys? Because if you can't see, I could, okay, what I'll do is I'll try to make them bigger then. Okay? Thank you for the next lesson. I'll do my best. Thank you, guys. All right. Let's do this. And that's it, actually. So thank you very much. I hope you enjoyed the lesson and learned a lot. Have a wonderful day, and thank you.